Hi students, welcome to your favorite physics channel Physics Philo. In the one video we have already discussed the different types of motion. What are the different types of motion which are happening around us, like a bike is running on the road, or you can say the earth is moving around the sun. These are the types of motion. But in this motion you can find when the bike is moving around the sun, it is like a linear motion, means it is it might be happening in the straight line, or if it is a bend the bike will move like this. But if you compare to this earth is moving around the sun, it is a different types of motions. That if we observe the swing in the park, the swing in the park, it is also one type of motions. Suppose if a child is sitting on the swing and we are just pushing it back and leave it, then we can find it is going some distance, again it is coming back, again going, again coming back. So this type of motion we can say the swing is moving around a mean position. That means there is a positions where it was started, only it is moving around this. These things we can easily understand if you observe this wall clock. In the pendulum clock you can observe the pendulum means it is a mass and it is just hanged with a rod. This is called a pendulum, and physics we assume this pendulum is like a string and mass system. In this wall clock we can find this pendulum, when it will run, it will go to some certain distance, again come to this mean positions, again go to certain extent, and then it is coming like this. That means the motion of this pendulum is happening around a single positions, which is called the mean positions. So these things we can understand clearly by these demonstrations. You can observe this. This is just a string and mass. In physics generally we assume a simple pendulum looks like this way. That means there is a thread which is called a massless thread, and there is a mass. We may call it simple pendulum. In this pendulum, this is a mass is there. If I will take this mass to certain height, then I will leave it. Then you can find this mass is going certain distance, again coming to this original positions, again going back, again coming to the original position, again going to back. That means these motions also like this pendulum, the wall clock pendulum, and this is the original positions which is called the mean positions, equilibrium positions. And this mass, this ball want to stay in this equilibrium position always if you won't disturb it. And when the motion starts around this mean positions, and the to and fro motion about a mean position is called the oscillations. So there is a variety of motion. And due to curiosity, we generally try to understand what are the forces which are acting on the motion, and all this physical system, all the different types of motions, it can be explained in terms of mathematics. And in the mathematical equations we always try to establish a physical system, and by finding the solution then we can manipulate this motion. And in physics today we will open the secret behind this oscillations. And on this connections, our topic today is damped harmonic oscillations. So before starting the topic, we should know all these things: oscillations, harmonic and damped. What I demonstrated, I have just explained. You can find the same mass is here, this is a string. So if I will just disturb this mass or take certain height to point A and leave it, then we can find this mass will come to position A to O, then O to B, and but at B it won't take rest, it won't stay at the B, it will again come back to O, and when it will return back to O, outside O also it won't set, it will go to the A. And here you can find it starts with the O, it will come to A, again come to O, again to B. So when this motion starts, suppose it is at t equal to 0, but when time increases you can find The next time when it will move towards A, this distance will not maintain, the distance will reduced and reduced. After certain time it is coming to 0. So in this demonstration, in this figure, we should understand two important things. One thing is how far the mass is going away from the mean positions. If this is mean position and the mass is here, that means the distance of the mass from the mean position is called the displacement. Remember, the distance of this mass from the mean position is called the displacement. And the force which try to bring the mass towards the mean positions, when we just start this body here and it will come to here and it will oscillating, that means there is some force which is bringing down this mass from this extreme position to mean positions. The force which bringing down the mass from extreme positions towards mean positions, it is called the restoring force. And displacement always away from the mean positions, and restoring force is always towards the mean positions. And these two terms are associated with this oscillation. So let's come to this title, damped harmonic oscillation. Oscillation we understood, the to and fro motion about the mean positions. Then what is the harmonic? The harmonic means when the restoring force that I have explained, it is proportional to the negative of the displacement. If displacement is this direction and the restoring force if it is opposite, then that type of motion is called the harmonic motion, harmonic oscillations. But remember, not always the restoring force will be proportional to the negative displacement. There is also other type of force when the restoring force is not proportional to the negative displacement. But those special type of force, when these conditions are applied, if our restoring force is proportional to the negative the displacement, this type of motion we can call the harmonic motion, or this type of oscillation we can call the harmonic oscillations. Also another concept of the harmonic, if the solution of any motion can be explained in terms of cosine or sine functions or e to the power I exponential functions, then only e to the power I form. E to the power I kt means if you open, then you will find also cos kt plus I sin kt. Of any solution, if it is expressed in terms of cos and sine, we can tell that this type of motion is also the harmonic motion, a harmonic oscillation. Then next come to the damped. The damped means decreased. You just remember, damped means decreased. So in this case, what is the parameter which is decreasing with time? Let's consider. So in this case we can find when it started the displacement is OA, OB. But when time increases, then this displacement OA it is reduced to OC. Then with increasing time it reduced to OE. Then with increasing time it reduced to OG, OJ, OL, and finally it comes to at rest. That means this distance, this displacement, it is reduced with time. And the maximum displacement all we are about, it is called the amplitude, or we can say if the amplitude of the oscillation is decreased with time, then we can say this is the damping motion, or this is the damped motions where the amplitude is decreasing with respect to time. So now we got all these things, what is damped, what is harmonic, and what is oscillations. Then in the damped case, the displacement decreasing with time, So now we will find the differential equations of damped harmonic oscillation. Actually, it is a beauty of the mathematics, we can say that with mathematics we can explain from very simple system to the very complex system. That means the whole process, whatever we have studied, this damped, harmonic, oscillation, all things can be mathematically explained nicely in the differential equation form. So let's discuss what is the differential equation of damped harmonic oscillations. Before starting to this differential equations, we need to know what are the forces which is there during the damped harmonic oscillations, and what are the forces which helps the mass to move around the mean positions, and what are the forces which always try to reduce the amplitude, because finally we are getting the mass is coming to at rest. That means some force is there which is reducing the amplitude. So let's discuss. So there are three types of force acting on this pendulum. There are three types of force acting on this oscillation of this simple pendulum. First is restoring force, which is proportional to the negative of the displacement that we have discussed. This is this pendulum. If the restoring force is towards mean position, displacement is opposite. This is the condition of also the harmonic motion. And here the restoring force, if you are talking about the harmonic oscillation, then this condition should be there. Fr is proportional to minus x. Yes, I want to tell something, I have missed it. Here you can see there is two system I have drawn. Why? Because in many physics book you can find where you are studying the damped harmonic oscillation, they have explained the same thing in the different system. This is called the spring and mass system. The spring and mass system, this is a rigid support and there is a spring and there is a mass. So if we drag this mass from this position to this position and level it, then you can find this mass is coming to here, again mean position, again negative extreme, again mean position, again negative extreme. In this way the mass will move around this mean positions and after some time it will come to the rest. And the same thing we have already seen in case of simple pendulum. Then it doesn't matter which system you are taking, but these two systems are same. But in our discussion, we will take into consideration this pendulum. So now in this pendulum, I told you that the restoring force is acting and the restoring force is proportional to the negative displacement, and thus Fr, the proportionality, we want to convert it to the equation form, then we can get Fr equal to minus kx, and this k is called the proportionality constant, and the k is the intrinsic parameter which associated with the spring or it is associated with the system. Therefore this k is called a force constant, or sometimes also it is called the spring constant. It is associated with the system. We cannot do anything, it is a constant value. And next come to the another force which is called the damping force. The force, it is called the damping force. In the damping force, we can find damping means, as I told you, damping means when the amplitude is reduced, this is called the damping. Damping means decreasing. So here we can observe here, when the displacement is in this direction, then there is a force, it is due to this medium. When this body is, I have started oscillating and it is coming to rest, what does it mean? That means in this medium air is present, and when this body is moving, the air is resisting this motion of this body. And this damping force, it arises due to this air resistance. And we have written the damping force is proportional to this velocity. Yes, we can understand in this small example. Suppose you are running a bike on the highway and your speed is 60 km/h. In the 60 km/h, then you will face some resistance, air resistance. Am I right? If we increase the speed to 80 or 100 km, it is a bike, it is not a car. When you increase the speed up to 100 km/h, then you will find more resistance from the air. That means the damping force depends upon the velocity of this body. Therefore, we have written the damping force is proportional to the dx by dt, yeah, velocity of the body. And the damping force, the air resistance always oppose the motion. If you are moving in this direction, then air resistance will always oppose to the motion of the body. That means the damping force is proportional to negative of the velocity, and if we will make it equality, then you can find Fd equal to minus b dx by dt, and the b is related to the medium, whether it is air medium. If you put the same pendulum inside the air in the water, then you will find a different damping factor. If we put this in this oil, then you will find a different types of resistance, and this constant b due to this damping force, it is called the damping constant, and it depends upon the medium. The restoring force, this k, depend upon the system, but the damping constant depend upon this medium where the motion is happening. Then now we got there are two force when the body is coming here, when it started the motion. So when it is coming towards the mean positions, then at that time the damping force is opposing the motion, so Fd is proportional to minus dx by dt. And when the motion start, when the displacement will start, you can find restoring force also dragging this bulb towards the mean position. Therefore, restoring force also is proportional to the negative displacement. So when you just observe, when the ball is coming to the mean position, so when the ball is coming to the mean positions, then it is not rest there, again it is coming to the negative extreme. And when it is coming to the again to the mean positions, it won't stay there permanently, again it come to the right extreme. And we can think if air is resisting to the displacement and also the restoring force it is against the displacement, then which force which is taking this ball from mean position to the negative extreme? When it is returning back again, it is not staying here, again it is going to the right extreme. This is nothing but the force of inertia. What we have studied earlier, there is inertia of motion and the inertia of rest. In the kinematics we have studied this Newton's law. The inertia of rest means if a body is at rest, it wants to stay at rest forever, if you are not applying any other force. And if it is body is in motion, it will be in motion forever if you want to apply any other force. This is called the inertia. Sorry. So here what is happening, when the body is in motion and coming to the rest, then the inertia of motion of the body, it is taking the body away from this negative extreme. It is the inertia who is taking the body from this position to away the extreme positions. That means the inertia of motion is in the direction of the displacement, but the other two forces, it is against the displacement. So I have written this inertia of force, it is proportional to the acceleration. As we know, F equal to mass into acceleration, that means force depend upon the inertial force, depend upon the proportional to the acceleration, and here also this inertia motion depend upon this mass. So we have used a mass as the proportionality constant, so we can write Fi inertia force equal to mass into acceleration. And in the mathematics, when we solve an equations, we want to bring the system to the equilibrium positions, yeah, in a balanced conditions, then only we start solving this problem. So in this case, at equilibrium, the inertial force which is in the direction of the displacement should be equal to the restoring force and damping force, then only the system will be a stable system. So in equilibrium condition, Fi equal to Fd plus Fr, inertia force equal to damping force for the restoring force, and the inertia force is nothing but mass into acceleration, m into d square x by dt square. And this here we can draw the damping force, it is also against the displacement, but the inertia force Fr, it is in the direction of displacement. Therefore, this inertial force should be balanced with the Fr plus Fd. Here m into d square x by dt square equal to your Fi equal to Fd minus b dx by dt, damping force. Then the restoring force is minus kx. It is called restoring force because it try to restore the body again towards this equilibrium positions, therefore it is called the restoring force. restoring force. Then md square x by dt square equal to minus this, we will try to bring this to the left side, then this minus and this minus become plus, the equation will become m d square x by dt square plus b dx by dt plus kx equal to 0. And this m just will divide with the m b and k, then we will find out this b by m and k by m. This b is called your damping constant, k is called the spring constant or force constant. Then we will find b by m dx by dt, k by m x equal to 0. Here this b by m we have to assume this is 2 beta, because for writing 2 beta it has some significance. Whenever we solve the equation we can find why we have written this is 2 beta. B by m equal to 2 beta, where beta is called the damping coefficient. This b by m we have written 2 beta, where beta is called the damping coefficient. This is damping constant b, beta is damping coefficient. And here k by m we have written omega square, because omega square means this is a angular frequency square. And why we have written is omega square? If we dimensionally solve this k by m, then only we can find the dimension of this k by m is coming to 1 by t square. This k is coming from here, force by displacement, and this is m. So force by displacement into 1 by m, force equal to mass into acceleration, force equal to mass into acceleration, m1 l1 t minus 2, then f by x, x means displacement. So this is your k equal to f by x. Then k by m, that means 1 by m, m1 l1, if we take it, then all the cancel, you will find t to the power minus 2. T to the power minus 2 means 1 by t to the power 2, that means 1 by t is frequency, then 1 by t to the power 2 means is frequency square, therefore we have written this omega square. So this k by m is omega square x equal to 0. So here beta is damping coefficient, omega is angular frequency, or sometimes we call this as natural frequency, that we will discuss in the first oscillations. So this equation d square x by dt square plus 2 beta dx by dt plus omega square x equal to 0, it is called the differential equation of damped harmonic oscillation. That means in this equation, this equations tells about this damped harmonic oscillation system. But whenever we solve it, then only we can find out what are the different solution of these conditions. This is just a system, and next we will discuss about what are the different types of solution for this differential equation of damped harmonic oscillation.